Hi, so I'm here, I'm based with the Astrophysics group, and I'll move to GPUs in a hydrodynamics code. That's all I'm going to try and focus on, mostly our problems. But my background is using smooth particle hydrodynamics to study star formation. We're interested in mostly where the most massive stars form in a star-forming region. They pump out huge amounts of energy back into the interstellar medium. This stirs things up and affects future star formation in their local area and has a huge impact on the RSE moving forwards. In the 10 years that I've been doing this, I've slowly spent more and more and more of my time developing code and less and less and less doing science. I feel lucky to have had the chance to do this. Many can't, and most people in positions like me are just forced to churn out papers, and they can't think long term. Very briefly, how does smooth particle hydrodynamics work? Well, we assign particles. They have mass. They move around. They don't bump into each other. They move straight through each other, although they do interact through pressure terms and gravity terms. But if you wanted to know a fluid property in this 2D representation, say here, you'd need to draw another one of these circles around this point. In my mouse, yes, you can. And then you would interpolate from all of the local particles using a smoothing function. So the particles in this red particle in the middle of this region has the heaviest weighting. Particles right near the edge have a very low weighting. So we average out the fluid properties. This is as opposed to in a grid code where you might have, you will have grids of fixed size and allow mass to flow between them. So the particles move, and this means for us it's amazing. We're interested in where the stars form, very dense regions. So we get a big clump of particles. We also have excellent resolution at the place that we're most interested in. Okay, we need to move this onto GPUs. GPUs run maybe 10 to 20 times faster than CPUs in terms of floating points operations per second. If you are actually porting a scientific code, if you achieve a 5 times speed up, I think you've done very well. And if you achieve that, you're matching the very approximate cost of a GPU node to a CPU node, and you're doing very well in terms of energy. So for the systems may be 5 times more expensive and use only twice as much energy. But if you can get 5 times more throughput, then you're doing really well. So now I start with our problems. So we're working with a code base that has been continually worked on since the late 80s by small numbers of people. Very often one person is the only person to interact with this code for a number of years in its history, but it's been optimized incredibly carefully and well for CPUs over that time, and it has huge numbers of different physics modules that we can add in. So moving to other codes has proven really difficult. And anyone coming in is typically on a postdoc, PhD, 3-year contract. In that much time, you need to choose a tool that works well and add to it, improve it, optimize it, do something bigger, better, publish. So no one's thinking long term. Okay. So our big problem is individual time steps. So I'm going to skip straight past this and go to a very, very quick video. So on the left, we have one of these star-forming regions. On the right, we have zoom-ins. So I'm going to skip right ahead to where we can begin to see stars forming. You can see stars popping out of this star-forming region, flying off in all directions, some staying centralized. And on the right, we can see if we zoom in on each of those stars, some of them are binary systems, some of them are multiple systems. We can see things are happening on very, very different timescales. And these are the areas we're interested in. So it turns out we can, for all the gas surrounding these stars, we can evolve maybe 4 million, 5 million, millions of times. Whereas for the gas in the very boring regions, once for every many millions of times we evolve everything else. So we have maybe 1,000, even though we might have 1 billion particles in our simulation, we're only ever really evolving several thousand of them at once. Times when we evolve the whole lot, but most of our time steps involve just thousands, and this does not work well with GPUs. Okay, so our approach is two-pronged. In the short term to medium term, we're trying to move just the most heavy physics code onto the GPU. And this works well for some of our simulations where the hydrodynamics is a small fraction of what we're doing. But for other simulations, we need to do a complete rewrite from the ground up. Many other groups are attempting it. No one has proven to me yet that they found the best way of doing this with smooth particle hydrodynamics. We're using OpenMP. I probably don't have time to justify my reasons, but it's already in the code. It's completely hardware agnostic, so it's a great tool. and it gets reasonably low level access, not quite as good as CUDA and HIP maybe. Okay, so all I really wanted to get across to you was what I'm working on, what those problems are, and maybe hopefully to make connections with any of you that have worked with GPUs or any problem with that faces anything that's in any way parallel to what I've just talked about. Thank you.
Thank you very much.